All right, let's talk about 1.4, which is a little bit about, we'll introduce a few identities in this section, and we'll talk a little bit more about calculating the trigonometric function values when you're given various pieces of information. So the first set of identities that we're going to discuss are the reciprocal identities, and these should be fairly obvious just from the definitions, right? So we talked about the fact that, for example, the definition of sine theta is y over r. Well, the definition of cosecant theta is r over y. So clearly sine and cosecant are reciprocals of one another, and this is just another way of saying that. The algebra might be a little confusing to you at first glance, but let me just show you, right? So 1 over sine theta by definition would be 1 over y over r, okay, because sine theta is y over r. And that's just 1 divided by y over r. In other words, it's 1 times r over y, which is just r over y. And r over y, by definition, is just cosecant theta, right? So really, the moral of the story is, if you know what sine theta is, then you know what cosecant theta is. You just flip the fraction over. Just flip it over. So if you know sine theta is 3/5, then cosecant theta is 5/3. If you know sine theta is negative 1/4, then cosecant theta is negative 4, right? And so sine and cosecant are reciprocals. Same thing with cosine and secant. And same thing with tangent and cotangent. Now you might think, well, why do we call these things the things that we do? Why don't we call the reciprocal identities cos, right? Like, why isn't like sine theta and cosine theta? Why aren't those reciprocal identities? Well, they're not reciprocals. They are co-functions of one another, and we'll talk about the co-function identities not today, but we'll talk about them a little bit later on. I think in chapter 2 we talk about the co-function identities, and so you'll see why sine and cosine are related, why secant and cosecant are related, and why tangent and cotangent are related via co-functions. But for now we're talking about reciprocals, right? Reciprocal identities. And so it just takes a little bit of memorization, right, to remember that sine and cosecant are reciprocals, cosine and secant are reciprocals, tangent and cotangent are reciprocals. So I gave you kind of a verbal example of this. I think it was almost these exact numbers, wasn't it? So let's say if tangent theta equals 3/5, what is cotangent theta? So I'll let you pause the video and see if you can figure out what cotangent theta should be. Okay, so the answer, of course, is that if tangent theta is 3/5, cotangent theta should be 5/3, right? Because tangent and cotangent are reciprocal identities. So cotangent is just, you take tangent and flip it over, right? You get 5/3. Another thing that we can talk about is where the trigonometric functions are positive and where they're negative. So, for example, right, we know that sine theta is y over r. That's just by definition. And r we always take to be a positive value because r is the distance from the origin to, some point on the terminal side of theta. So r is always a positive value. Okay. Consequently, the sine, okay, this is going to be kind of difficult to say. I should have chosen a different trig function, but consequently the sine, positive or negative, right? The sine SIGN of the sine function SINE, right? The sine function. So the sine of the sine function is going to be totally dependent on the sine of y, because r is always positive, right? So if y is positive, then sine is positive. If y is negative, then sine is negative. Okay? And so what that tells you is that if you're looking at quadrants, if you're looking at this in terms of quadrants, right? So sine is going to be positive here in quadrant 1 because this is where our y values are positive, right? So sine is going to be positive in quadrant 1 and in quadrant 2, right? Because this is where the y values are positive, right? Whereas in quadrants 3 and 4, sine is going to be negative, right? Sine is going to be negative in quadrants 3 and 4 because y is negative in quadrants 3 and 4. Okay, we can go through a similar line of reasoning for the other 6 trig functions. Obviously, cosecant has the same signs as sine does, right? It's positive in quadrants 1 and 2, negative in quadrants 3 and 4. Cosecant and secant, on the other hand, are a little different, right? Cosecant and secant depend on x, right? Cosecant is x over r, or sorry, cosine is x over r, and secant is r over x. And again, r is always a positive value, so cosine and secant have whatever sine x does. That means that cosine and secant are going to be positive in quadrants 1 and 4, right? Because that's where our x values are positive. They're positive here in quadrant 1 and quadrant 4. Quadrant 1 and quadrant 4. So cosine is going to be positive in quadrants 1 and 4. Whereas, of course, it's going to be negative in quadrants 2 and 3. Okay, same thing goes for secant, right? And then finally, for tangent and cotangent, these things are positive if and only if x and y have the same sign, right? Because tangent is y over x and cotangent is x over y. So if x and y are both positive, then tangent's going to be positive. If x and y are both negative, then tangent's going to be positive, right? Because a negative divided by a negative is a positive. But if x is positive and y is negative, or if x is negative and y is positive, then tangent is going to be negative, right? So tangent is positive here and here, right? Because here we have a positive x and a positive y. Here we have a negative x, but also a negative y, so that's going to make tangent positive still down there. In quadrants 2 and 3, that's where tangent's negative. Okay, because we have a negative x but a positive y, so positive divided by a negative is going to be negative, whereas here we're going to have a negative divided by a positive, and that's still going to be negative. So this is how this is the best way to remember, right, all of this information. So the acronym that we use is all students take calculus, right? Calculus, right? All students take calculus. What does that mean? Well, all means that all of the trig functions are going to be positive in quadrant 1, right? All of the trig functions are positive in quadrant 1, right? Sine and cosecant, cosine and secant, tangent and cotangent, they're all positive in quadrant 1. In quadrant 2, on the other hand, notice that tangent is negative and cosine is negative, but sine is positive, right? So the S in students stands for sine, right? Sine is positive here. Sine and cosecant, right? If we look in quadrant 3, tangent is positive, cosine is negative, sine is negative. So in quadrant 3, the only thing that's positive is tangent, right? So tangent is positive in quadrant 3. And then finally, if we look at quadrant 4, tangent is negative, cosine is positive, sine is negative. So the only trig function that's positive in quadrant 4 is cosine. Well, cosine and secant, right? But the C stands for cosine, right? So cosine is positive in quadrant 4. So you can remember this by all students take calculus, right? All of the trig functions are positive in quadrant 1. Sine is positive in quadrant 2. Tangent is positive in quadrant 3. And cosine is positive in quadrant 4, right? All students take calculus. Okay. And then, of course, as I've been mentioning, right, if a particular, trig function is positive in some quadrant, then its reciprocal is also positive in that same quadrant, right? So each trig function has the same signs as its reciprocal function. So to give an example of this, let's determine the signs of the trig functions for each of the following. So this is example 2, I guess. So for each of the following, let's do 24 degrees. So I'll walk you through this one. This is a really easy one, right? Because 24 degrees is in quadrant 1, isn't it? Right? 24 degrees would be, maybe something like, if I can get this pen to right, something like that would be maybe 24 degrees, right? So 24 degrees is in quadrant 1. That means all of the trig functions are positive there. So if we're looking at sine and cosecant, right, they're positive. If we're looking at cosine and secant, they're positive. And if we're looking at tangent and cotangent, they're positive, right? All of the trig functions are positive in quadrant 1. Let me give you a different example. Let's do negative 24 degrees. So with negative 24 degrees, that's going to put us here, right? So there's negative 24 degrees. So we're in quadrant 4, right? 24 degrees was in quadrant 1. Negative 24 degrees is in quadrant 4. So if we're in quadrant 4, not all of the trig functions are positive. Only cosine and secant are positive. The rest of them are negative, right? So sine and cosecant would be negative. Cosine and secant would be positive, and tangent and cotangent would be negative. Okay? So let me give you one more, and this one I'll let you pause the video and see if you can do this one on your own. So figure out the signs of the trig functions for 120 degrees. You don't have to give the value, just the signs. Okay, so here's my solution. We've got to figure out which quadrant we're in. Now 120 degrees, it's more than 90 degrees, so I know that I'm not in quadrant 1, but it's less than 180 degrees. So I know that I'm not like beyond this point. So I must be here in quadrant 2 somewhere, right? So 120 degrees is maybe something like that. But it's definitely in quadrant 2. So what trig functions are positive in quadrant 2? Well, all students take calculus, so sine is positive in quadrant 2, right? Sine and therefore cosecant as well. So sine and cosecant are going to be positive. Everything else is negative, right? Cosine and secant and tangent and cotangent are negative. Okay? So that's that. Let's look at a different kind of problem. So let's identify the quadrant, or if there's more than one, the quadrants of an angle theta that satisfies the given conditions. So let's see. So let's identify the quadrants of an angle theta that satisfies the given conditions. Let's do, let's say that cosine theta is greater than 0 and tangent theta is less than 0. So when we say that cosine theta is greater than 0, that's the same thing as saying that cosine theta is a positive number, right? Cosine theta is positive. And when we say tangent theta is less than 0, that's the same thing as saying that tangent is negative, right? So in which quadrant or in which quadrants is cosine positive but tangent negative? Well, cosine is positive in quadrants 1 and 4, but in quadrant 1, tangent would also be positive, and we need for tangent to be negative. So that must be quadrant 4 then, right? So the fact that cosine theta is positive tells us that we're either in quadrant 1 or quadrant 4. But the fact that tangent is negative tells us that, okay, so it must be quadrant 4. Right? So this tells us that we're in quadrant 1 or quadrant 4. But then this one tells us that it can't be quadrant 1, right? Can't be quadrant 1, must be quadrant 4. That's the only possibility. So let me give you another one. And I'll let you pause the video and work this one out on your own. But let's do sine theta less than 0, cosecant theta less than 0. So pause the video, see if you can work that one out. Okay, so here I think we have a couple different solutions. If we're looking at sine theta needs to be negative. Well, sine is positive in quadrants 1 and 2, so it's negative in quadrants 3 and 4. So this condition here tells us that we're either in quadrant 3 or quadrant 4. Now, in addition to that, we need for cosecant theta to be negative. Well, but cosecant is just the reciprocal of sine, right? And reciprocal identities have the same signs. So cosecant theta less than 0, that also happens in quadrant 3 or in quadrant 4. So this one we have two solutions, right? Quadrant 3 or quadrant 4 would do the trick. Okay, so we'll see some more examples in a second of why it's important to know what the signs of the trig functions are in different quadrants. But for now, let's move on and talk about another fact about trig functions. So trig functions have the following ranges. So remember, the range is the set of outputs of a function. So when we say that sine theta has range -1 to 1, by the way, this is interval notation. You should be familiar with that from your previous algebra classes. If you're not familiar with interval notation, then let me just say briefly that this means that the output values are going to be between -1 and +1. It can be any real number between -1 and +1, and the square brackets indicate that they could be exactly equal to -1 or exactly equal to +1. If we used parentheses instead of square brackets, then that would be saying that the outputs could be between -1 and +1, not including the -1 and the +1. But anyway, so if we're saying that the set of outputs for the sine function are between -1 and +1, or sorry, if we're saying that the range is -1 to 1, then we're saying that all of the outputs of sine fall between -1 and +1. So you can never, it doesn't make sense to say, for example, that sine of some angle is equal to 5, right? That's outside of the range of the sine function. Same thing goes for cosine. They have the same range. Tangent and cotangent, well, their range is all real numbers, okay? And then secant and cosecant, their range is almost all of the real numbers. It's all of the real numbers except for the numbers between -1 and +1. And that should make sense when you think about the fact that secant and cosecant are the reciprocals of cosine and sine respectively. And so if the range of sine is -1 to 1, then the range of its reciprocal is everything else. Okay? So I'm going to prove, I'm at least going to prove this fact to you, right? The range of the sine function is -1 to 1, and then you'll kind of see, I think, why that is the case for the rest of the, or why the rest of the trig functions have the ranges that they do. But so here's the idea. If you think about some angle, which we'll call theta, we can choose any point on this side and draw a little right triangle that has those values x, y, and r. Now if you think about sine theta, what's sine theta? It's y over r, right? By definition, that's what sine theta is. It's y over r. Now, y is a leg of a right triangle, whereas r is its hypotenuse. And it's a well-known fact that the legs of a triangle both have to be shorter than the hypotenuse of that triangle, right? So the legs of a right triangle have to be shorter than the hypotenuse of the right triangle. So the hypotenuse is always the longest side of the triangle. That means that y is always going to be smaller than r whenever you have the situation. The one exception is if the terminal side of your angle theta happens to fall right on an axis. So if it's a quadrantal angle, right? So if this is your angle theta, right? Well, now you don't really even get a right triangle. You just get this kind of segment. And y is the same thing as r in that case, right? So either you're going to have y strictly less than r, like in this case here, or you're going to have y equal to r, like in this case here. In either situation, you have a smaller value in the numerator than you do in the denominator. So it would be something like 1/2 or 2/3 or something along those lines, right? That number is going to be less than 1, right? This is always going to be less than 1, unless you're in this situation here, in which case y equals r. If y equals r, if these are the same number, if it's like 2/2, well, that equals 1, right? So sine theta is always less than or equal to 1. On the negative side of things, right, so I drew this triangle in quadrant 1, so y was positive, r was positive, but you could also have an angle down here, let's say, right, down here in quadrant 3, in which case y would be some negative value, right? Y would be less than 0. But r would still be positive, and the absolute value of y would still be less than r, okay? It's just that you're going to have a negative value. A negative divided by a positive is negative. Okay, so then consequently, sine theta is going to be bigger than or equal to -1. So, in other words, sine theta, regardless of the value for theta, sine theta has to be between -1 and +1. Same thing goes for cosine, okay? Cosine is x over r. The same thing does not hold for tangent and cotangent, because tangent is y over x and cotangent is x over y. And you could have, you know, any value. I mean, you could have like a really small value for x and a really big value for y, right? So you could have some situation like this, where this is theta. So you have a really small value for x and a really large value for y. So if you're looking at y over x, you can have a big number over a small number. That's going to be a big number, and we can make it as big as we like. So tangent can go off to infinity, right? There's no bound on how large tangent can get. Same thing with cotangent, right? With secant and cosecant, notice that, you know, if cosine theta is between -1 and 1, well, how would we say this? So a little trick from algebra is that if you take the reciprocal like that, then the inequalities have to change direction, although that doesn't really work, does it? Because we'd be saying this is bigger than 1 but less than -1, so it doesn't really work out to say it that way. Here's what we could do. We could split this. We could say, alright, so we've got this and we've got this. Now I'm going to take the reciprocal of both, right? When you take the reciprocal of cosine, then you have to switch the inequality. Switch the direction of the inequality, okay? So then, and then notice that 1 over cosine is secant. So what we're saying is that secant theta has to be less than or equal to -1, or secant theta has to be bigger than or equal to +1. Okay? So if cosine is squeezed between -1 and +1, then secant is everything else, right? Secant, because just due to the nature that secant is the reciprocal of cosine. So that's the idea there. Anyway, but the moral of the story is this, right? This is the moral of the story. And again, at this point, I hope it goes without saying that if you need to pause the video to write stuff down, then pause the video and write stuff down, right? But this would be a good thing to write down and commit to memory and stuff, right? But this is the moral of the story. So let's practice with that a little bit. So let's determine whether each statement is possible. And I'm just going to write out a bunch of these, and then I'll let you write them down and work it out. But let's determine whether each statement is possible. So cosine theta equals 2.5. Cosine theta equals 0.5. Cotangent theta equals 2.5. Okay, I think I'm going to be using the same values for each of these. Cosecant theta okay. So go ahead and give the video a pause and try to see which of these statements are nonsense and which of these statements are acceptable. Okay, so I'm going to go through and put a check mark next to the ones that are appropriate, and then I'm going to cross out the ones that are not. So cosine theta equals 2.5, that's not possible, right? Cosine has to live between -1 and +1, so that doesn't work. Cosine theta equals 0.5, yeah, that could happen. Cotangent theta equals 2.5, yeah, that could happen, right? The range of cotangent is -∞ to +∞, so cotangent can be any real number. So 2.5 works, 0.5 works, that's perfectly acceptable. What about cosecant? Cosecant theta equals 2.5. That works, right? Cosecant theta can be almost any real number. It just can't be between -1 and 1. So 2.5 is outside of that, so that works perfectly well. But cosecant theta equals 0.5, and that doesn't work, right? Because cosecant has to be either less than -1 or bigger than +1. It can't be between -1 and +1. Okay, so that's how that works. Okay. Here's another important example. This goes back to the idea of understanding about where trig functions are positive and where they're negative and stuff. Let's suppose that theta is in quadrant 3 and that cosine theta is -2/3. Let's find the values of the other 5 trig functions. So I'm actually gonna ask you to not pause the video. I'm gonna walk you through this because there's a common mistake that students make on this type of problem that I really want you to avoid. Okay, so the common mistake that students make is that they come into trig class having learned a little bit of right triangle trigonometry, which we'll talk about in chapter 2, right? But then they try to use their right triangle trigonometry to do this kind of problem, and they end up with the wrong answer. They're going to end up off by a sign. So let me show you the wrong way. So I'll show you the wrong way first, so that hopefully you don't make this mistake. But oftentimes what students will do is they'll just draw some right triangle kind of willy-nilly. They'll just draw some kind of bogus right triangle. And they'll say, all right, cosine theta is x over r, so maybe they'll say this is x over r, and then they'll say, if I want to find the values of the other 5 trig functions, then I need to solve for y, which is, true, right? So far, so good. That's not a problem. So they'll say, so x squared plus y squared equals r squared. So they'll say 4 plus y squared is 9. So y squared is 5. So y is the square root of 5. And then immediately they'll start to, sorry, let me pause this real quick. All right, sorry about that. Anyway, so they'll say y equals square root 5, right? And then they'll start to list off their trig functions. They'll say, all right, so I was given cosine, but maybe I can write down, sine theta is y over r. So they'll say it's root 5 over 3, and then cosine theta was given, and then they'll say, tangent theta is y over x, and so forth, and they'll write down their answers. This is wrong. You're only off by a sign. Really, y should be negative root 5 here, okay? Because when you get to this step where you're taking the square root, remember that you have to have the plus or minus sign. So you're going to get y equals plus or minus the square root of 5, and you have to make a decision. Is it going to be the positive square root of 5, or is it going to be the negative square root of 5? And in this case, you should choose the negative square root of 5. And you can't tell that by drawing this picture, right? So this picture is no good. On a test or a quiz, if I ask you to if I ask you this kind of question and you draw this picture, I'm going to take a couple points off, at least a couple of points, because this picture does not help you figure out if y should be positive or negative. What you need to do is draw the angle in standard position. So this is the right way to do the problem. So what you should do is draw the angle in standard position, right? So you give yourself a coordinate plane, and you have to decide which quadrant is theta in. Well, you're told blatantly here that theta is in quadrant 3, so you know that theta is in quadrant 3. So that's the correct picture, right? That's the correct picture. And that's important because now when you go to, sort of form your right triangle out of this, then you can see clearly that y is going to be a negative value. You're down here in quadrant 3, so y has to be negative, right? So I'm not going to redo all of this work, but you would do this work, and then you would conclude, okay, y is negative square root of 5, right? X was negative 2, and r is always a positive value, right? So r was positive 3. That's the correct picture, okay? And when you draw it correctly, when you draw the angle in standard position and you get the angle in the correct quadrant, well, then you can list off your trig function values pretty easily. So here are the correct solutions. You'd say sine theta, as it turns out, is negative root 5 over 3. Cosine theta was given to us. It's negative 2/3. Tangent theta. Tangent theta is y over x. That would be negative root 5 over negative 2. The negatives will cancel and just give you a root 5 over 2, a positive root 5 over 2. Cosecant theta is just the reciprocal of sine theta. So that's negative 3 over root 5, which is perfectly acceptable to me. You can leave your answer that way. If you want to rationalize it, then you should get negative 3 root 5 over 5. So either one of those answers would be fine. Secant theta is going to be negative 3/2, and cotangent theta is going to be 2 over root 5, or in other words, 2 root 5 over 5. Okay, so those are the correct solutions. Okay. So I want to give you, in this section, a couple more identities that will be useful to us. We tend to think of these identities as kind of like fundamental identities, in the sense that they're identities that are going to come up over and over and over again, that we use quite often, especially in calculus. So the first set are these Pythagorean identities here, right? So the Pythagorean identities are these ones, right? So we have three different statements, right? So first of all, sine squared plus cosine squared is 1. Second of all, tangent squared plus 1 is secant squared. And then third of all, 1 plus cotangent squared is cosecant squared. And I'm going to prove at least one of these to you. So here's our claim. Our claim is that sine squared theta plus cosine squared theta equals 1. And let's prove it. Well, we know that sine is y over r. So sine squared is y over r squared. We know that cosine is x over r. So cosine squared is x over r squared. Well, I kind of went about this backwards. Let me try again. Let me start over. Really what we would say is this. We would say x squared plus y squared equals r squared. This is something that we know from the Pythagorean theorem. So we know this from the Pythagorean theorem. If we divide through by r squared, and then factor out, not factor out, but we can take out that square, right? We can call this x over r squared plus y over r squared, and then r squared over r squared is 1. And there you go. That's where the statement comes from, right? Because x over r is cosine. So this is cosine theta squared. Y over r is sine, so this is sine theta squared. And by the way, just as a matter of notation, cosine theta squared, we usually write the exponent right there. So we just call it cosine squared theta. But this thing and this thing mean exactly the same. Same thing goes for any other exponent. But there you go. There's the proof. But yeah, just in general, if you have some trig function like any of the trig functions, but we'll use tangent as our example. If you have a notation that says this, tan to the n of theta, that really does just mean tangent theta to the nth power, right? So anyway, but that's that one. You can see how you would get the rest of them. You always start with this Pythagorean theorem, x squared plus y squared equals r squared. But then you can divide through by different quantities. Like if we divide through by x squared instead of dividing through by r squared, we're going to get 1 plus y over x squared. Y over x is tangent, right? So we're going to get 1 plus tangent squared equals r over x squared. R over x is secant, right? So we would get 1 plus tangent squared equals secant squared if we divide through by x squared. If we divide through by y squared, then we get cotangent squared plus 1 equals cosecant squared, right? So those are all Pythagorean identities. So that's that. And then the last set of identities that I want to talk about in this section are the quotient identities. So the quotient identities are, they give us a way to think of tangent and cotangent in terms of sine and cosine, right? So tangent theta, it turns out, is the same thing as sine theta divided by cosine theta. And cotangent theta, turns out, is the same thing as cosine theta divided by sine theta. So let's prove that. So the claim that we want to try to prove is that tangent theta equals sine theta over cosine theta. So let's prove it. So I'm going to start with sine theta over cosine theta. By definition, sine theta is y over r, and cosine theta is x over r. In other words, we have y over r divided by x over r. That's the same thing as y over r times r over x. And the r's cancel, right? And so we just get y over x. Y over x, by definition, is tangent theta. And so there you go, right? Tangent theta is just sine theta over cosine theta. Same thing goes for cotangent theta. Actually, for cotangent theta, we could make it even quicker because we could just say, well, cotangent is the reciprocal of tangent, right? So if tangent is sine over cosine, then cotangent is cosine over sine. So let's look at a couple of examples using these identities. So let's use identities to find cosine theta and tangent theta if sine theta is negative 5/12, sorry, negative root 5 over 12. So sine theta is negative root 5 over 12, and cosine theta is less than 0. So we could find cosine theta and tangent, cosine theta and tangent theta the same way that we did example 5, right? So we could use a similar line of reasoning as we did when we did example 5. But this one is asking us specifically to use identities to do this. So, so see if you can use the quotient and Pythagorean identities to figure out what cosine and tangent are. So go ahead and give the video a pause and see if you can work that out. Okay, here's my solution. So I'm given sine theta, and I'm asked to find cosine theta. I'm also asked to find tangent theta, but I'll worry about that later, because notice that if I can find cosine theta, tangent theta is just going to be sine over cosine. So once I've found this, I can get tangent theta really easily just by using that quotient identity. Tangent is sine over cosine. So as far as finding sine is concerned, as far as finding cosine is concerned, I have an identity that relates sine to cosine, and it's this Pythagorean identity up here that we proved, right? Sine squared plus cosine squared equals 1. So, we're going to say sine squared theta plus cosine squared theta equals 1. Sine is negative root 5 over 12, so we've got negative root 5 over 12 squared plus cosine squared theta equals 1. And then we can just solve for cosine theta, right? So if we square this value, we're going to get positive 5 over 144. Then if we move that over to the other side, 1 is the same thing as 144 over 144, right? And 144 minus 5 would be 139. I'm not sure why I chose such nasty values, but that's life, I guess. So cosine squared theta is going to be 139 over 144. And then we take the square root of both sides. When we do that, remember we have to have a plus or minus sign. So square root of cosine squared is just, of course, cosine. So we have cosine theta equals plus or minus square root of 139 over 144. So we have to make a decision. Is it going to be the positive square root or the negative square root? And up here we're given a clue, right? We're told that cosine theta is less than 0. In other words, cosine theta is negative. So we're going to choose the negative square root. We're going to say cosine theta is negative root 139 over 12, right? So I'm taking the square root of 144. It's just 12. So get negative root 139 over 12. I wonder if there's any perfect squares we can pull out of 139, or if that's maybe a prime number. Let me see. Square root of 139. No, it's prime. Or maybe not prime, but there are no perfect squares that go into 139. So that's as good as it's going to get. So there's cosine theta. And now that we have cosine theta, we can get tangent theta pretty easily. We can say tangent theta is sine theta over cosine theta. So that's going to be negative root 5 over 12 divided by negative root 139 over 12. You flip and multiply. The negatives will cancel. You should end up with root 5 over root 139. You could rationalize this by multiplying by root 139 in the numerator and denominator, in which case you get square root of 5 times 139, 695. So you get square root of 695 over 139. So that would be the answer, that the way that the book would present it. This answer would be okay, I think, on a test or a quiz. But this is how the book's going to have it. But anyway, so that's tangent theta. Okay, so that's that. Again, you didn't have to. The reason we solved this using identities is because the directions told us to do so, right? They told us explicitly use identities to do this. But if you were just told, if you weren't told that, if you were just told find cosine theta and tangent theta if this, then you totally could have done this the same way that we had done number 5. The trick is to make sure that you're drawing theta in the correct quadrant. So let's just practice doing that, right? So to get theta in the correct quadrant, note that sine theta is negative. Sine theta is negative in quadrants 3 and 4. So you know that theta has to be either in quadrant 3 or quadrant 4. You also are told that cosine theta is negative. Cosine theta is negative in quadrants 2 and 3. So the only quadrant where both sine and cosine are negative is quadrant 3. That must mean theta is here in quadrant 3, right? The rest is history, right? So the rest you can kind of figure out on your own. Let me give you one more example, and then we'll call it good on this section. So let's use identities to find sine theta and cosine theta if cotangent theta is negative 4/3 and theta is in quadrant 2. Okay, so let's see if we can do this. Use identities to find sine theta and cosine theta if cotangent theta is negative 4/3 and theta is in quadrant 2. Okay, so let me show you something that would be wrong, right? Here's something that would be wrong. To say something like, well, I know that cotangent theta is cosine theta over sine theta. And since cotangent theta is negative 4/3, that must mean that cosine theta is negative 4 and sine theta is 3, right? Cosine theta is negative 4 and sine theta is 3. Right? After all, theta is in quadrant 2, and so cosine is negative there, sine is positive there. So you might be tempted to say that that's your answer. Cosine theta is negative 4 and sine theta is 3. Unfortunately, that doesn't work, right? Because remember that sine and cosine live between -1 and +1, right? So the answers here that we're looking for have to be between -1 and +1, and so this doesn't quite work. So we need a different approach. It's not that this identity isn't true. We'll talk about this a little bit later once we get our answers. Okay, so we'll come back to this identity and show that this identity does still work, but it's just that the ratio of sine to cosine needs to be 4 to 3. That doesn't mean necessarily that cosine is 4 and sine is 3. So let's find the actual values of cosine and sine. So we have to try to use a different identity. I think what I can do so we have a Pythagorean identity that involves cotangent. It says that 1 plus cotangent squared is cosecant squared. So if we can use that identity to solve for cosecant, well, sine is just the reciprocal of cosecant, and so then we'll have sine, right? And once we have sine, well, then we can use this identity to find cosine, right? Or we could use a Pythagorean identity or something like that. There are multiple ways that we could do this. But so let's do this, right? So let's say 1 plus cotangent squared theta equals cosecant squared theta, right? So that's that Pythagorean identity. We're given that cotangent theta is -4/3. So what we have is 1 plus -4/3 squared equals cosecant squared theta. -4/3 squared would be 16/9, and then 1 is the same as 9/9. 9 plus 16 is 25, so this is 25/9 equals cosecant squared theta. Oh, this works out pretty nicely, right? So now we take the square root. Okay, and we're going to get cosecant theta equals either the positive or the negative square root of 25/9. Which should it be? Well, we know that theta is in quadrant 2. Sine is positive in quadrant 2. That means cosecant is also positive there. So this time we're going to take the positive square root. Square root of 25/9 is 5/3, right? Anyway, we chose positive because theta is in quadrant 2. Okay, well, if cosecant theta is 5/3, then that means that sine theta is 3/5, right? Because they're reciprocals of each other. So there's sine theta. So now that we have sine theta, we can say, all right, it is in fact the case that cotangent theta is cosine theta over sine theta. Moreover, we know that sine theta is 3/5. We also know that cotangent theta has to equal -4/3, so it should be the case that cosine theta over 3/5 equals -4/3. And then we can solve for theta this way. So if I multiply both sides by 3/5, the 3's will cancel, and I get cosine theta equals -4/5. Okay, so it is still the case that cotangent is cosine over sine. It's just that that doesn't necessarily mean that cosine is -4 and sine is 3. Actually, what's the case is that cosine is -4/5 and sine is 3/5. And notice that when you divide this by that, you do still get -4/3, just like we would expect. Again, more than one way to skin a cat, though, right? So this isn't the only approach. It's like from here you could have used a Pythagorean identity, right? You could have said sine squared plus cosine squared equals 1, and then replaced sine with 3/5, solve for cosine that way, right? So that's another way that you could use identities to do the same thing. But that's that. I think that's all I have to say about this section, so we will see you in the next one.